This video is about a kx modification of the basic antidifferentiation rules. This is just a shortcut for u-substitution in the cases where our u-substitution is just k times x. So here's the idea. Let's say I'm taking the derivative of e to the 5x. So if I were to use the chain rule to take this derivative, and that's the appropriate rule, I've got an inside function, and my inside function is 5x. According to the chain rule, the derivative of e to the 5x is e to the 5x times the derivative of the inside by the chain rule. Now the derivative of the inside is just 5 because we have a constant times x. So we end up with 5 times e to the 5x. So when I differentiate e to the kx, in general I'm going to get k times e to the kx. Because we get e to the kx times the derivative of the inside by the chain rule, and the derivative of a constant times x is just the constant. Well, if I'm trying to undo that operation, rather than multiplying by the constant like I would due to the chain rule, I have to divide by the constant. So here is our kx modification for the e to the x rule. So the antiderivative of e to the x is just e to the x plus c. If I replace that x with a kx, the rule is exactly the same, or almost exactly the same. I get the antiderivative of e to the kx is e to the kx. So I replace the x with a kx. But if I were to take the derivative, I'd have to multiply by k. Since I'm taking the antiderivative, I divide by k. And that's actually true for all of our rules. Like every single rule can be rewritten where x is replaced by a kx. Now there's only a few where it actually makes sense, and it's usually with those composite functions. So let's look at our trig functions. Those are good candidates for this. So the antiderivative of sine of x is cosine of x plus c. So let's see what the kx modification should be. Well, the antiderivative, that should be negative cosine of x plus c. Sorry about that. The antiderivative of sine of kx is negative cosine of kx, so the angle stays exactly the same. But because there's a k multiplying that by that x, you divide by k. Antiderivative of cosine of x is sine of x plus c. So the antiderivative of cosine of kx is this. Antiderivative of cosine of kx is sine of kx. So you replace the x with kx. But then if I were to take the derivative, I would have to multiply by k. If I'm taking the antiderivative, I have to divide by k. So all of our rules can be modified in this way. But we really only tend to use this modification for e to the kx, a to the kx. I mean, we could use it down here, but it's pretty uncommon to use it there. But we would use it for e to the x, a to the x, and then all of our trig rules can be rewritten with that kx modification. So let's look at an antiderivative where we apply this. So let's say somebody asks you to find the antiderivative of 4 times e to the 2x minus sine of, let's say, 3x plus secant squared of x over pi dx. Well, each of those is a kx modification. Here, k is 2, because I'm multiplying the x by a 2. Here, k is 3, because I'm multiplying the x by a 3. And here, it's not pi. The factor multiplying x is 1 over pi. Okay, so if I want to take the antiderivative of something that looks like this, I could do a u sub for each of these. I could let u equal 2x, and then du would be 2 dx, and then I'd have to divide by the 2. Hey, that's where that 2 comes from, that 1 over 2, that 1 over k comes from a u sub. We could do that, or we could just do this rule. So here, this is what I suggest, just do the rule. Rather than doing u sub every time for each one of these, it's much easier to do this. So you bring the 4 down, the antiderivative of e to the 2x is e to the 2x. Since there's a 2 inside, you divide by 2. Then you say to yourself, what's the antiderivative of sine? It's negative cosine. So you have negative cosine of the same angle. So put that 3x back inside and then divide by the 3. And then over here, you take the antiderivative of secant squared of kx. Antiderivative of secant squared of something is tangent of that something. Since there's a k inside, you divide by the k, but dividing by 1 over pi is the same as multiplying by pi. And we add c. And of course, we would simplify that. 4 over 2 gives us that. Now, I just alluded to the fact that this is a shortcut for u-substitution. So let's just prove it for a particular function. We looked at the sine and cosine substitutions. Let's do it for a different one. Let's see. We just did secant squared. How about secant times tangent? We've got the antiderivative of secant of kx times tangent of kx dx. Well, I could use the u sub where u is equal to kx, then du is equal to k times dx. And then if I'm getting dx by itself, I have to divide both sides by k. So then I replace everything up here with u's. I have to write everything in terms of u instead of x. So that's secant of u, tangent of u, and dx ends up being 1 over k times du. So the antiderivative of secant of u, tangent of u du times 1 over k. And so we get 1 over k times the antiderivative of secant of u times tangent of u, which is secant of u plus c. But then you back substitute. So you replace u with kx and then add c. Isn't that exactly what I told you the answer would be? If your x's have been replaced by kx's, the antiderivative of secant times tangent is secant of kx. And then since there's a k inside, you divide by the k rather than multiplying by it. You would multiply if you're taking the derivative. You divide because you're taking the antiderivative. If you want to undo that with a u sub, you can go through this process every time. But as you can see, it's relatively long, and you kind of know what the answer is going to be because the derivative of kx is k. So to undo multiplying by k, we divide by k. Okay, so that is that rule. I just want to use it to state all of the new rules. And then we'll look at examples of each one. This will be very brief, I promise. So I've got the antiderivative of e to the kx. The antiderivative of e to the x is e to the x plus c. So we replace x with kx, and then we divide by k. If we were taking the derivative, we'd multiply. Since we're taking the antiderivative, we divide. If I've got a, oops, I wrote 2. I was thinking of a specific value of a. If I've got a raised to the kx power, well, according to my rules, the antiderivative of a to the x is a to the x divided by natural log of a plus c. So I replace my x with kx, and then don't forget to divide by k, so multiply by 1 over k. So we get a to the kx over k times natural log of a plus c. So just as a couple of concrete examples, we've got the integral of e to the 5x. That'll be e to the 5x divided by 5 plus c. The integral of 2 to the 3x is a kx modification of the a to the x rule. The antiderivative of 2 to some power is 2 to that power divided by natural log of 2, natural log of the base plus c. Put the 3x back inside, and don't forget to divide by the 3. Okay. So if I have the antiderivative of cosine of kx, antiderivative of cosine is sine. You want to keep those angles the same. And since we're taking antiderivatives, we divide by k. The antiderivative of sine is negative cosine. Replace the x's with kx's, and we divide by k. The antiderivative of secant squared is tangent. The angles need to stay the same. And since we're replacing x with kx, we divide by k. Then you've got secant times tangent. Antiderivative of secant times tangent is secant. Divide by k there. Antiderivative of cosecant squared is negative cosecant. Oh, excuse me, that's wrong. It's negative cotangent plus c. Replace the x with a kx. Divide by k. So we did cosine, sine, secant squared, secant, cosecant squared. Now we want to do the antiderivative of cosecant of kx times cotangent of kx. The antiderivative of cosecant times cotangent is negative cosecant. You replace the x with a kx, and then you divide by the k. Okay, so those were our first 6 rules. Derivative of sine was cosine, derivative of cosine was negative sine, derivative of tangent was secant squared, derivative of secant was secant times tangent, derivative of cotangent was negative cosecant squared, derivative of cosecant was negative cosecant cotangent. And then we introduced these new rules in the last video. The antiderivative of tangent turns out to be negative natural log of the absolute value of cosine. If you replace x with kx, you can do that, but you've got to have a 1 over k out front. I really would have written a 1 over k, I just didn't leave enough space that time. Cotangent is similar. If you do the u-sub, you write cotangent of kx as cosine of kx over sine of kx, and do a u-sub, you'll get natural log of the absolute value of sine of kx plus c. Replace the x with a kx, and then make sure you divide by k. And then the other two, we've got cosecant of kx and secant of kx. Those are those sort of strange ones where we had to multiply by secant plus tangent over secant plus tangent to get a rule for this, so that we could do that u-sub, that logarithmic u-sub. And then this one we had to multiply by cosecant plus cotangent over itself and do the u-sub. When we did that, well, the antiderivative of secant was natural log of the absolute value of secant plus tangent plus c. So if we replace that x with a kx, it's going to be exactly the same. Just have a 1 over k out front. And then for cosecant, we got a negative natural log of the absolute value of cosecant plus cotangent. We replace the x with a kx. You get a 1 over k. So I hope through doing that exercise, you get the pattern. So when you see this problem, when you see cosecant squared of 5x, I hope that doesn't trip you up at all. You say, oh, that's a kx modification. The antiderivative of cosecant squared is negative cotangent. Replace that x with a 5x, the angle stays the same, and then there's a k inside, so we divide by k out front. So it's just a simple modification that accounts for this u-sub so that you don't have to do that u-sub every time. It's such a simple u-sub. If the u-sub is, if the function inside your function is just a constant times x, when you take the derivative, you multiply by the constant. When you take the antiderivative, you just divide by it. And that's what all of these rules show. And I really don't even have these memorized. What I have is my basic rules memorized and then the kx modification and how it works. Like, I know that. And I would prefer that you learn that.